Hey guys, welcome to a new video. In today's video we're going to look at a Leetcode problem, and the problem's name is find bottom left tree value. So in this question we're given the root of a binary tree and we have to return the leftmost value in the last row of the tree. So this is a straightforward description. You have to find the last row, and inside that last row what is the leftmost value, you have to return it. So in this case 1 is the output, and in this case 7 is the output. Now let's take a look at these examples and see how we can solve this question. So let's take the first example. You're given the root of a binary tree 2, 1 and 3, and your answer is 1 because that is the leftmost value in the binary tree. So you need to find the leftmost value in the last row of the tree. So this is the last row and this is the leftmost value. So you know you have to reach the last row. So you have to traverse through all the nodes. There are two techniques, DFS and BFS, to traverse through the nodes inside the binary tree. So DFS is depth wise. You access the depth first. And BFS is level order traversal. You access all the nodes in one level and you go level by level. So first you explore this and next you explore this level. So in this video, let's solve this using BFS. So in BFS, first you are at the root and then you access all the nodes in the current level. You go to the next level, and while going to the next level, you traverse from the left to the right. So you access all the nodes in that level from left to right. But here we need the leftmost value inside the last row, right? So what happens if we traverse from right to left of every level? So the last node you visit will be your answer. So let's take this example. So to implement BFS, you need a queue. So you are at the root, so add the root. So 1 will be added. All its node will be connected as a subtree. So I'm taking the topmost element in the root. Now we go to the next level. So how do you go to the next level? You start from the right, and now we pop that element out of the queue. So after popping, we have 1. We check if 1 has a right child. Yes, 1 has a right child. So add that into the queue. And now you are at this level. You access this, and you are at 1. You checked its right child. Now you have to check its left child. If it has a left child, yes, so add it into the queue from back. Now you access both the nodes of 1, so eliminate that. Now from the queue, pop the first element. It is 3. Now for 3, check its right child first and then the left child. Check if 3 has a right child. Yes, it has a right child. So 6 will be added at the end of the queue. Now we added the right child, add its left child. Check if it has a left child, yes, so add it into the queue. Now you access both the left and right child for 3, so you eliminate that. Now take the top element from the queue, it is 2. Add its right child, it does not have a right child, so it won't be added. Add its left child, yes, it has a left child, so add it into the queue in the end. Now we access both right and left for 2, so eliminate that. Now we are at this level. Now take the topmost element, it is 6. Check if it has a right child. No, it does not have a right child. Check it as a left child. No, it does not have. Now we access both left and right, so remove it from the queue. Now take the topmost element, it is 5. Check its right child. It does not have a right child, so it won't be added. Check its left child. It has a left child, so add it into the queue. Now we access both left and right, so remove it from the queue. Now get the topmost element from the queue. It is 4. Get its right child. There's no right child for 4. There's no left child for 4. We access both of them, so remove it from the queue. Now the root is 7. Check its right child. There's no right child. We check its left child. There's no left child, so remove it from the queue. Once the queue is empty, whatever is the last element we processed, so this is the root, right? So root will be here. So return root.val. Root.val is 7, so 7 is the output for this equation. Now let's take a look at the code to implement BFS. Coming to the function given to us, this is the function name, and we are given the root of the binary tree, and the output is an integer representing the last row's leftmost value. So like I said, we are going to implement this using BFS. So to implement BFS, we need a queue. So let me declare it. This queue is going to store tree nodes. I'm going to name it queue, and it will be implemented as a linked list. Now to start off, we need to add this root into the queue. So initially, root is here, so it has its left and right connections. So into the queue initially, using the add method, add the root. Now like we discussed, we need to iterate until the queue is empty. So using a while loop, we keep on iterating, and this while loop's condition will be until the queue is empty, until queue dot is empty. So until the queue is empty, this will happen, and once the queue is empty, it comes out of the while loop. And now if queue is not empty, there is at least one element present inside the queue. So using the poll method, get that element and remove it from the queue. So I'm going to use the root itself and using the poll method on the queue. So the poll method will return the first value present at the beginning of the queue, and it will also remove it. And now we have the root. So if root is here, first we need to add its right child. So before adding the right child, we have to check if right is present or not. So if root.right is not equal to null, only then add it into the queue. So queue.add of root.right. Now again we have to do the same for the left child of the root. So root.left If it is not null, only then add that into the queue. Queue.add of root.left. So make sure that you're first adding the right child and only then adding the left child. And this while loop will happen for all the elements inside the root. And finally, once queue is empty, you come out of the while loop and you have to return the last visited node. The last visited node will be here. So root will be here, right? So return its value. So return root.value. Now let's try to run the code. The test cases are being accepted. Let's submit the code. And our solution is accepted. So the time complexity of this approach is O of n because we are iterating all the nodes inside the tree at least once. And the space complexity is also O of n because we're using a queue to solve this question to implement BFS. That's it guys. Thank you for watching and I'll see you in the next video.